you. First of all, I would like to thanks Tech Me Buddy as well as Acharya Narendra Dev College for giving me the opportunity to represent my talk on the National Workshop on Biomedical Data Analysis with the topic of fundamental of statistics. So yeah, my name is Sumeet Patiyal. I'm a postdoctoral computational scientist, a visiting fellow in the Cancer Data Science Laboratory at CDSL in the NPI NIH USA Bethesda campus. So today I will talk about fundamental of statistics. So I will keep it very easy so that you can understand it. So I would like to keep the mathematics as less as possible. So yep. So okay. So this is the content of my slides. It seems very much, but I have not included so much things in it. So first I will start with different definitions of statistics. Then we'll talk about nature and types of data, which we tackle in biological field as well as in different fields, as for example, commerce, arts, and other fields. Am I audible, right?
Yeah, right. Very well.
Yes.
Great. So yeah, so then we'll move to measurement scales, then population and sample, then type of statistics that is used in these days in different fields, types of distributions. I won't go into deep of types of distribution because it itself is a very vast field, very deep field. So I will just give you a glimpse of it, and then we'll go for normality and outlier check, the skewness and kurtosis, which is very important in these days. Then we'll go for correlation and regression. We'll also see the measurement of associations. We'll go for logistic regression, then the odds ratio and the risk ratios. Different parameters which is used in the field right now, especially in case of machine learning, which is called sensitivity, specificity, and the ROC curve. And I'll end with the talk. I'll end the talk with the statistical test for the hypothesis testing. So there are different definitions which exist in the field right now. So according to the NCERT textbook, this is a branch of mathematics dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. So what you find in every single definition is the collection, analysis, interpretation, and presentation. So for example, in case of Oxford Dictionary, it says that it's a practice or a science of collecting, analyzing the numerical data in large quantities, especially for the purpose of inferring proportion in the whole from those in the representative samples. So I will explain what is population, what is samples at the end. So I just for the fun activity, I go to ChatGPT. I ask what is the statistics for according to the ChatGPT. So it says the same thing as NCERT books. It's a collection, analysis, interpretation, presentation, as well as it added as an organization of the data. So what I have highlighted over here is that statistics plays a crucial role in various fields, including science, business, economics, social sciences, and many other fields, providing tools to understand and make informed decisions in the face of uncertainty. So, reading all this, understanding all this, my own definition of statistics is an intuition. It's basically an understanding which let you feel and understand the data and help you to convey your thoughts about the data to the people, which makes you so you can basically make people understand what you have think about the data, what you have interpret from the data. So in my opinion, statistics is nothing but just an intuition, nothing else. So we'll move to nature and type of data. So there are two kinds of nature. Two kind of data which is available, which is structured and unstructured. Structured is the one which basically has defined columns, defined rows. So you can just pick a simple value using a column, using an index of rows or index of column. Unstructured data is something you cannot. It's not structured well in case of rows and columns. It's not metrics. It could be anything. For example, if you see the electronic health record given by the doctors, it's unstructured data. You have to take the information out of the data, right? Using their interpretation, using their notes. So two types of data that we consider in the analysis is categorical as well as measurement data. So the categorical data is just for the qualitative purpose. So you just check the quality of the data. I mean, for example, you want to see if you want to rank if you want to rank the athletes, so you are basically ranking them based upon the qualities, right? So it's just the qualitative data. In case of measurement, you can measure the so for example, for a runner, you can measure that how many meter or how many distance he runs or she runs in a few minutes or in a few seconds. So this is called quantitative data. So measurement scale. So don't worry, Einstein never taught measurement scale. This is just just AI made slide. So basically, there are two kinds of. So you can further divide the categorical data into two, which is called nominal and ordinal. So nominal is different from ordinal in just one way, that nominal data cannot be ordered, and if the ordinal data is basically ordered. For example, you can see the status of your professor. So so there is an order. First we come assistant professor, then there is associate professor, then there is professor. So this variable, the position of your professor, is basically nothing but the ordinal variable. In the case of measurement data, is something which you can measure. For example, you can measure the height, you can measure the BMI, you can measure the blood pressure, you can measure the age. Something you can measure is called interval and ratio. So just few examples of the categorical data I would like to give here is like hair colors, which is like brown, red, and black. So this is a nominal. The nucleotides ATGC, the adenine, thymine, guanine, and cytosine. These nucleotides are nothing but the nominal variables. Eye color is black, brown, green, blue. These are nothing but also a nominal variable. Socioeconomic status, since it has the order of low, middle, and high, they are nothing but the ordinal variable. Followed by gender, male, female, it's a nominal. Disease, mild, moderate, severe, it has its order in it, so it's ordinal. And at the end, genotypes, which is called HH, or small capital H, small h. So yeah, so you guys are familiar with genotypes and phenotypes, I guess, right? So some examples of the measurement data are nothing but like cholesterol levels, the height, the age, the FPKM and the RPKM values that you have considered when you do some gene expression analysis. I think Manas will take care of it after the session. So FPKM and RPKM is nothing but fragment per kilo million base pairs, and RPKM is reads per kilo millions. The number of expressed genes and time to complete a homework assignment is just a measure of data. Something we can measure is the measurement data. So the population and sample, there are two terms which we basically use in statistics. A population is a large sample of individuals or the items that consideration in a statistical study. And sample is nothing but just a part or subset of a population from which the information is collected. For example, I give you examples. So the total number, if you want to analyze the height of the students in the entire entire college of yours, so it's very difficult because the college is very huge and you cannot go to everyone and just take the height of everyone, and it will take a long time, and then you do the analysis. It will take a long time. So what you can do, so that's population. But what you can do, you can take you can basically take samples randomly from each class. For example, the person with the shortest height, the person with the longest height, right? So using these data, you can make your hypothesis. You can make your interpretation that okay, so this is the range of height belongs to, so the student belongs to the it belongs to your college, right? I hope I'm clear, right?
Yes, sir.
Okay, thank you. So followed by the type of statistics, there are two kinds of statistics that people basically use. Is called descriptive. It is just to show the organizing and the summarizing information, nothing else. I mean, and in case of inferential statistics, it is something, these are the methods for drawing and measuring the reliability of conclusion about population. So basically you'll use some tests here which based upon your test, based upon your p-values, based upon your understanding, you can say that if the population or if the samples under considerations are basically different from each other or not. So to basically draw conclusions from your analysis is called inferential statistics. So descriptive statistics are the summary statistics. So I've just given some examples here that you can using which you can understand. So the common measures of the frequency is nothing but your count, your percent, your frequencies that you can use. And common measure of central tendency you have read in your high school or in your 11th and 12th class. So basically mean, median, and mode. So mean is basically the average. The median is something above which you have equal number of samples, and below which you have equal number of samples. So and mode is mode is the most occurring number, most occurring value, the most occurring element in your data. So for example, if you take like first 5 values in the consecutive number 1, 2, 3, 4, 5, so your mean would be nothing but 1 plus 2 plus 3 plus 4 plus 5 divided by 5, right, which is equal to 3. So same with the median. So if you have like 5 values, 1, 2, 3, 4, 5, you can just divide the samples in 2 different parts, based upon which you can say that the equal number of samples exist above and below the value. For example, if you have 1, 2, 3, 4, 5, so your median is 3, because below 3 you have 2 values, above 3 you have 2 values. So it's the middlemost value, we are using which you can basically divide your samples into categories. So the most interesting and the most important measure is the dispersion. So based upon which you basically define your data. So any important technique for data extraction, you basically use this kind of dispersion. So for example, your PCA, your TSNE, and your UMAP plots and your UMAP values. So these all are based upon the variance. So you're basically trying to cover as much as variance in the data. So this measure is very important. So it contains range, which is nothing but the difference of your highest and the lower value in the data. Your variance, your standard deviation. So there is a relationship between variance and standard deviations. The standard deviation is nothing but a square root of variance and interquartile range. So it is just between the two quartiles, quartile 1 and quartile 3. So quartile 3 is something which are having values greater than 75%, and your first quartile is basically having the value which are less than 25%. So you basically use a formula and you have found the interquartile range, and you explain that how much variance and how much variability is existing in your data. Which is this is very important, when you use your gene expression data. For example, you always if you have 2 different groups, for example, you have a patient as well as you have a healthy group. So if you want to compare it, you should have a very good variation in case of in case of your disease as well as healthy individuals. Only then you can make something out of it. Otherwise, you won't be able to conclude, or you can say that this expression is very important or not. So inferential statistics is basically 2 kinds of things that you can consider in this. So one is like hypothesis testing, in which you basically just test your hypothesis. Hypothesis is something, a statement you want to make about a data. There are 2 kind of hypotheses you basically consider. So one is null hypothesis, denoted by H0, and the other one is alternative hypothesis, which is H1. So in this statement, or how do you define the null hypothesis? This is a kind of a statement which is supposed to be rejected. So you always hypothesize in the opposite manner when you consider a test. So these are the different tests. So for like Z test, the F test, and T test, ANOVA is analysis of variance, Wilcoxon side rank test, Mann-Whitney U test. These are tests which are very widely and very usually used in case of statistics as well as in case of biostatistics. So you have seen a number of papers in which they have used T test or Mann-Whitney U test, as well as for the Wilcoxon and Z test. Another very good example of inferential statistics is the regression analysis. So there are different kinds of regression analysis these days: linear, nominal, logistic, ordinal, based upon the value they want to. So these all are varying only based upon the dependent and independent variables. So dependent and independent variables I will explain later. Other than that, there are also called non-linear regressions. So these days, number of non-linear regressions are existing, such as there is something called random forest regressor, there is a support vector machine regressor, there's something like that. So if you want to explore this, you can Google it, and you can see that there are ample of regression analysis exist. So I just take this screenshot from the Google. I just type the type of distribution and it gives me this. Even I was not aware that this much of distribution does exist these days. So yeah. So in case of plasma distribution, there are a number of types of distributions which are available, but the one which is very interesting, which is ideal and which is being used in different kind of studies and which exists in the real life is your normal distribution, which follows the bell-shaped curve. Other than that, there are called binomial, there are Poisson, exponential, Bernoulli, uniform. There are different kind of distributions which exist, and based upon this distribution, so the statisticians were able to evolve or able to generate different kind of test to basically test the hypothesis. So these all are linked. Even if you want to understand the type of distribution, this would take more than 2 lectures or 3 lectures, because it's a very deep field basically. So this is an example that how you can track how you can understand the distribution of your data, right? So first you have to see that if your data is discrete or continuous. So discrete is nothing but the integers 1, 2, 3, 4, 5, and the continuous is everything. It's like 1, 2, 3, 4, 5 with the decimal points 1 point, 2 point, 3 point, something like that. So if your data is continuous, you see that if your data is symmetric or asymmetric. So if your data is symmetric, you go for like, is the data is clustered around a central value, and if it yes, how likely or how we have outliers. So see, you can see if you have a very low number of outliers, you go for the normal distribution. So what you will see when you have a normal distribution, when you have a data, the data should have a continuous values. It should have a symmetric distribution along the median. So if you have a median in between, so you should have equal number of samples below the mean and after the mean. So something like that. So for example, we can see this is a normal distribution. So this is what we call, this is the mean value. And around the mean value, you should have equal number of samples here and equal number of samples here. So this is the normal distribution, which is very, very common in the biological studies. Again, so you can see that if the cluster is not around the central value or the mean value, you will go for the uniform or a multimodal distribution. So these are the kind of distribution that you can see. They're called binomial. You have like either uniform, discrete, geometric, negative binomial, hypergeometric. So this is also very important. Hypergeometric is the one which basically used in the population studies. Population statistics. So you have triangular, normal, logistic, Cauchy. You have exponential, log normal, gamma, as well as the minimum extreme. So these are the kind of distributions which are basically available, and you can just track based upon your kind of data, and if it follows the symmetry and how's the outliers. So based upon this, you can basically track, and you can see that which kind of distribution your data may have followed. But just not by seeing this you can do this. You have to check the normality. You have to check the distribution of your data based upon different tests which are available, right? So in that case, the checking of normality is your hypothesis. So here, the most widely used distribution. So one I've said, like normal distribution, we can see that as a distributive bell-shaped curve. You have the maximum value around your central value, which is a mean, and your sample is equally distributed against your variance. So when you say like this is your first variance, second variance, and third variance. So as it has been said, in normal distribution, your 99% of data is basically contained between the mu plus minus 3 sigma. So basically the 3 proportions of your various standard deviation, all data is basically contained, right? So it is this bell-shaped curve. It can modeling natural phenomena, as I've said, that most of the things which exist in the biology or most in the physics is basically following the normal distribution. So it says like modeling natural phenomena, and then there is height, weight, IQ, test score, etc. Least square fitting or propagation of uncertainty is examples of these examples for this distribution. The certainty test, it is also a very normal list, this is also a very normal test or very widely used test, you can see. So the only difference is that it is based upon the samples and not on the population. So it's shorter, fitter than the normal distribution. And when you have a small sample and don't know the water population variance, you'll use the standard distribution. For example, they also have binomial. There is only two outcomes: so success or failure. So if if the probability of success is p, the probability of failure would be 1 minus p. Something like coin toss probability head and tails, right? The Poisson is something I don't know if you guys have used something as a tool called Max, so which is nothing but to just measure the peaks in your data. So I don't know if you guys are aware of it, but that tool is completely based upon the Poisson distribution. So it basically it's a discrete distribution, as it gives you the probability of a number of events in a fixed interval. For example, if you want to see the number of calls coming in a call center in a defined interval, if you want to find the probability of number of calls coming to a call center in a 30 minutes, then you will see, then you have to consider that data as a Poisson distribution. And at the end, there is an exponential distribution, which basically models times between the events. Nothing, how much time will go by before a major hurricane hit the Atlantic seaboard. So something like that. So now the question arises that if your data is normal, you see your data is something it's all continuous variables, and it basically and you have a mean value and you have a standard deviation, and you see that the data is lying between that. But how you can say that your data is actually following the normal distribution, right? For that, there are different procedures. So what is called graphical procedure, you can use different plots such as histogram and box and whisker plot and normal quantile plot. I hope that that Alok and other people have told you about the code in the based upon that you can basically draw the histogram or the box plot or the normal quantile plot, which is called QQ plot. But they're also called exact methods. So these are the methods which you can give your data to these methods, and it will tell you if your data is normal or non-normal, or if it follows the normal, or it follows the binomial or Poisson or your exponential distribution based upon a p-value. So it's a test which basically tests your hypothesis that if your data comes from a normal distribution or not. So there are different methods which exist in nature these days. So this is called Kolmogorov-Smirnov test, Shapiro-Wilkie statistics test. There's called Anderson-Darling test. So this Anderson-Darling test, the last one, is a very it's a very accurate method. It is the latest method as compared to Shapiro and Kolmogorov. But you can use this method, and based upon this test, you can see that if your data has come from a normal distribution or not. So the null hypothesis for this, as I've told you, you define your null hypothesis H naught, your alternative as H1. So there could be one null hypothesis, but your number of alternatives could be anything. So if I say, so all these method uses a null hypothesis and says your data comes from the normal distribution. So if your p-value is greater than 0.05 here, only then you will be able to accept the null hypothesis. Otherwise, you have to reject your null hypothesis. So if your p-value is coming out to be more than 0.05, then you'll say that your data is basically following the normal distribution. Otherwise, it does not come from the normal distribution. So there could be other alternatives too. So it could come from the binomial. It could come from your Poisson. It could come from negative binomials or something like that. So using these methods, you can basically test if your sample is coming out to be normal or not. And why it is important, I'll explain it later, why it is important to check the normality of the data. So this is the method, and you can see this is nothing but we have just taken the sample of age, which basically range from 1863, and we want to see the frequency. This is the frequency. You can see this is the histogram. As you can see, this data is quite well what do you say, well bell-shaped curve, right? Same when you see the normal thing, and then you basically define the your box plot. So box plot is like, this is the minimum number, this is the maximum number, This is nothing but your first quartile, this is second quartile, this is third quartile. Your second quartile is nothing but your median. So this is the median. If you see, this is nearly about 34.5, and you say that this is nearly about 34.3. So this is nothing but but no, this is the mean, but this is the median. This is the median, which is also very close to 30, 31, 32, I guess. So what if you have an outlier in your sample? How will you see that? How will you remove it, right? So to do that, you just draw a box plot. So there is one observation which is like 147, which could be wrong. I don't know. If someone is having a range of having a age of 147. So this could be a mistake. So if you take this data and run your analysis, you won't be able to get accurate results, because of this mistake. Your entire analysis could be ruined. So you just draw a box plot, and you'll see that there is only one point which is existing outside, which is basically lie very, very far from your box plot. So you can see that this is the outlier. This could be a mistake. So when you are entering the data, so this you should do when you should check your data always, that if it has outlier or not. So then you have to see that if this is outlier is basically exist on its own, or this is your mistake. So this is your QQ plot. So basically, this is a plot between your observed value and expected normal value. So if your data lie on this straight line, this line, then your data is following exact normal distribution. For in this case, this is not. I mean, some of the values are following normal distribution, but most of them are not, because they're deviating from your reference. So you can,
Yeah, hi.
yeah, you sure.
Somebody have raised a hand.
Uh, okay, sure. You can ask question in between. I don't have any problem with that.
Can you please explain QQ plot a little bit?
Okay, sure. So basically, as I've said, the QQ plot. So this is your observed value. These are the value you already observing in case of when you are collecting the data, right? But in case of expected normal value, so normal distribution is already well defined, right? And it is so, and the based upon the normal distribution. If I'm having, so it is already defined based upon your degree of freedom, that if I'm having samples, if I'm having, like, suppose if I'm having a sample of 1,000 people with a range of 18 to 63. So what could be their expected values based upon that? So basically, it should follows this straight line when you found about the quantile normal plot. So your sample should fall on this line if your data is following the normal distribution. Otherwise, it won't fall. It won't fall on this. For this example, this data is not following the normal distribution because it is not following on this line. Am I clear?
Okay, thank you.
Yeah, thank you. So you can also find your outlier based upon the Mahanabalis distance. It is nothing but you can see that it's basically calculation of distance. Your two variables. So your variable 1, variable 2, and even you can see that if you're so this is basically following some distribution here, but this is the outlier. So it's just a method to find your outlier. That's it. So this is basically this is nothing but your formula to find the distance for each point, where x is your actual value, your mu is nothing but your mean, and s is nothing but your standard deviation. So yeah, so next we should understand about the skewness. So skewness is nothing but it basically measure the lack of symmetry. So if your data is following a normal distribution, then it should be falling like this. So this is a normal distribution where your samples is basically available around your mean. So your beta 1 is basically nothing but it's the representation of skewness. So beta 1 is equal to 0. But what if your values are towards towards less than the mean? So your beta 1 is greater than 0, and you'll say that is a positive skewed. And if it is less than 0, then it's a negative skewed. Nothing else. That's it. So this is the measure that you can use. You just calculate the moments. Based upon the moments, you just say that if your data is or your normal curve is skewed or not. So your second moment is nothing but your variance. So these are just the formulas. As I've said, that I won't go into go into your this mathematical formulations. So you know that the xi is basically sample, x bar is nothing but your mean value. So you just this is the formula of this is the formula of your variance, which can also be calculated using the values as well as the moments. Next, kurtosis is also it is also a measure of symmetry, where you can see it basically measures the peakedness of the frequency curve. So this is your 3 different curves. The difference in the curves is the peakedness of the peak. So basically the peak, how the peak is. This is a flat peak. This is a it's a good peak, and it is a little bit flattened. So one of the like a platykurtic distribution, when you have your beta 2 value is less than 0, which has a lower and a wider peak around the mean. So this is your mean. So it is around the mean, you have a wider peak. The mesokurtic is this one, basically a flat top distribution. Your beta 2 value is 0. And lipokurtic has a more acute peak around the mean, which is like beta 2 is greater than 0. So beta is basically a measure of kurtosis. So it's nothing but moment 4 divided by the square of moment. So this is nothing but your variance square minus 3. So yeah, so now let's move on to the correlation division. Now we have understood the concept of that how the data should look like, that how the data is available, and how we should see the data set. Now we should move on to the correlation and regression problem. So these are the most simplest and most important thing that we should do with our data, to understand that we should proceed with the data, or we should proceed with the hypothesis that we're considering right now. So we'll start with the correlation. So there are different kind of correlation exist. So the most importantly, you have most widely used is the one called Pearson correlation, which is just a linear relationship between two continuous variables like y and x. They should both be metric and both be linear. Metric means nothing but measurable. So anything you can measure. For example, you can measure the distance. You can measure the height. You can measure the age. So there should be a positive correlation, but they're always outlier, right? So as your age increases, your height should be increasing for a certain period of time. So it should follow a positive correlation for a small period of time. But what if you cannot measure the values, and still you want to compare? You want to compare the correlation. So there is something called rank correlation. So this is a Spearman's rank correlation, which is applied on a non-normal distribution, and you can find the correlation between the rank as well as the metric values. For example, I remember when I was studying the statistics, my professor gave me an example of so he gave me an example of beauty with the brain. So suppose if you want to see that for example, the girls who are beautiful and who are having a brain. So if you want to, you cannot measure the beauty, right? You cannot measure the beauty, but you can rank them, right? The most beautiful, less beautiful, and like something like that. And you can measure their IQs, and based upon you can see that if there is a positive correlation or not, something like that. So other than that, there are different correlations like multiple correlations, which are using you should all be metric. You have, but this is a multivariate. You have one dependent variable, which is y, and all of them are dependent, like x1, x2, and x3, something like that. So you just measure the metric correlation. Then there is a partial correlation coefficient, is nothing, but it is also a relationship between two different variables, x and y, x1 and x2, but you have a different other variables, or maybe confounding variables, which basically impact x and x2 indirectly. So you want to fix that, and you want to see that if there is a positive or a negative correlation between your x1 and x2. There is other called correlation ratio, which is like curve, which is which is represented by eta square. This is nothing but to find a correlation between two or more variables, which is depicted graphically by anything other than a straight line. So if the relationship between your x and y is not linear, then what you should do? I mean, I don't know. I mean, which correlation you should apply? So there is something called correlation ratio, which you can apply, and you can see that if the correlation between your y and x is basically a positive or a negative one, or there is no correlation, of course, which is always exist. There is also called non-linear correlation, which is based upon specific models. The model could be anything. I mean, it could be square, it could be it could be cube root or something like that. I mean, the relationship between your x and y could be anything other than other than the straight line, which is like y is equal to mx plus c. So in order to measure the association of between different samples, what you do, you can apply different methods. It's like chi-square for the large sample, Fisher-Exact test for the small sample. Both measure this association between your variables. But when you have a very large sample, your Fisher-Exact test won't work. Actually, it will work, but it will take a long period of time, because the formula that it uses in the back end basically takes time to converge, and it won't converge for a very large sample, or it can stuck into infinite loop. So it's better to use the chi-square, which is nothing but a shortcut. Basically it's a shortcut basically, rather than the Fisher-Exact nest. So you can test your hypothesis, you can interpret your results from here, but it won't be as exact as Fisher-Exact test. So what if so this is data type. So if your data type is nominal by nominal, if you want to compare two different variables which both are nominal, which both are categorical, right? You can calculate the contingency coefficient, you can use phi and Kramer's V, you can use lambda, you can find uncertainty coefficient. So this is the one. Uncertainty coefficient is the one which is widely used. So other than that, if you have ordinal by ordinal, so you can use that. There is like gamma coefficient, there is like Somers-D coefficient, this kind of Tau coefficient. The gamma is the one which is very widely used. If you have like nominal by ordinal, so then you will use chi-square test. If you have like nominal by interval, you can use kappa, risk, McNamara, and eta. Eta is the one which is widely used these days. What if you have a ratio by ratio or interval by interval? So I was talking about which is like metric by metric. So you can use like Pearson correlation, you can use a Spearman correlation, you can use multiple correlation, you can use partial correlation, something like that. And all these are examples that I have explained there. So this is nothing but just the extension of what I have just represented to you. So this is the thing that I was talking about, that this is test you can use. And for example, you want to measure gender versus blood types. So if you want to see if there is an association between your male and female and the different blood groups, A, B, O blood group, then you can use the nominal. I don't think there is any correlation exist, but maybe, I don't know. If you want to use to see that endochroplasia and parental age versus risk of disease, Fragile X syndrome, number of repeats versus the severity of the symptoms. In case of nominal by ordinal, you can see AMD. This is nothing but this age macular disease, which happens in the eye. You can find the association between your allele genotype versus risk of disease, type of cancer, and survival rate. But nominal by interval ratio, you can see the examples as an ethnic origin, which could be European or American or Indian, for example, Asian, for example, versus the amount of lactose produced in the intestine. And for ratio by ratio, this could be the most interesting one for you guys, because yeah, of course, when you do analysis in the biology, you will use only these kind of correlation. You will never encounter such correlation in your life. So this would be like, okay, is there any question?
Yeah, could you please repeat again nominal by interval slash ratio?
Okay, so nominal by interval. So one of the variable is your categorical. So if you want to see the association between your categorical as well as your your countable measure, right? So if you have like some, so this is ethnic origin, right? This is your nominal variable. Ethnic origin could be anything. For example, if it could be like European, it could be American, it could be Asian, it could be anything, right? It could be something you cannot measure, but you can just provide a value to, right? Like it could be, so if you have a population from the American, you have a population from the European people, you have a population from the Indian people, and then you measure the amount of lactase produced in the intestine. So this is which is called like interval one. So it's basically the one which you can measure, right? You can just take the blood and you can see that how much lactase the person is producing from the European and your American and the Indian people, and you can see, is there any association, is there any link between the ethnic origin or the amount of lactase. Maybe you can find out that, okay, the people from the India is basically producing high lactose compared to European and the American, right? So just to see the association between your two variables, the nominal as well as the interval one. So for this, you use kappa, you can use risk, you can McNamara, you can eta, biseral and point biseral, something like that. So this is the one. Eta is the one which is widely used. You can find the eta. So eta is nothing but your coefficient that you can be based upon that you can say if it's possible, it is positively correlated or negative correlated, or it is not
All
correlated
right.
at all. Yes.
Okay, all right. And also about Bissell or point Bissell, what are these? Also the methods to
Yeah.
determine the
Yeah,
correlation.
yeah. These are all the methods. These are all the method biserial and the point biserial, the methods which are basically used. I think this biserial and point biserial are the one that the latest method as compared to the other methods. Eta, McNamara, Risk, and the Kappa, they came very early stages, but the biserial and the point biserials are the new methods. And I've seen some papers these days which people are basically using it to basically compare your nominal with the your interval or ratio data sets,
All right, thank you.
for sure. Then at the end, you can see ratio by ratio, interval by interval. So you can see RNA-seq gene expression profiling. You can compare the expression of two different genes. For example, you want to see the tumor suppressor gene to oncogenes. You can see that if they're highly correlated or not. Ideally, they should not. I mean, they should be negatively correlated. So in civil condition, treated versus non-treated during development, affected versus non-affected, something like that. So this is thing that you want, these table that you can use to basically compare, or you can make your mind based upon your data set that if you should follow, you can further take these variables or not. One thing I would like to put pressure here is that you never use correlation for your predictions. Correlation is just something which already exists. It's a fact. But you never use correlation for the predictions. You always use regression for the prediction, because for the regression gives you give you a formula, a unique model behind it, which you can use to make the prediction. But correlation never gives you a different. Correlation never gives you a model or a formula which you can use to basically make the predictions. Always use regression in that. So next method is we will talk about regression. So regression is nothing but to just see the relationship between a dependent and independent variables, nothing else. So it's a statistical procedure for predicting a value of a dependent variable for an independent variable when the relationship between the variables is linear, right? So this comes with a condition that the relationship between your dependent and the independent variable should be linear. They should follow a linear distribution. So this is the model. So this is like nothing but you must have read a straight line equation in your school, which is like y is equal to mx plus c. So there's nothing. This is called y mx plus c, nothing else. So if you have so this is the beta naught is the value at 0 time point. Your beta 1 is the coefficient for x with which it is varies to basically define y, and this is nothing but the error term. So y here is your dependent variable and x is your independent variable, because y is always dependent upon x. As the x varies, y varies. But x is not dependent upon y. X can take any value. So that this is how you basically defines your dependent and independent variable. So this is the dependent variables, time since then, death, and independent variable could be like sodium potassium ratio, or this is the other term. So this is basically a very simple model. So if you if you see that if you have two variables and you draw it and it follows a very positive correlation, and if you want to see that if you want to predict that if this if you have some unknown value and we want to see that what value y it will take, so you can use this formula. Okay, so suppose suppose you have some sodium potassium ratio which is unknown to you. If you want to see that what is the time since death for a patient, you can just use this method. I have example for it. So if you want to see the relationship of a body temperature and interval in the gray tree frog, so this is how you do it. So you see here, this is negatively correlated. As the temperature increases, your ICI seconds decreases, right? So this is negatively correlated. So if you see this so this is the formula. ICI is equal to beta naught 1 plus beta 1 and body temperature and y. So ICI is your dependent variable and body temperature is your independent variable. So you can just put any value here, and your beta naught and beta 1 is already defined. If you have this coefficients with you and error terms with you, you can just you can always find the ICI value. For if you can see this this curve, you can see that this is negatively correlated. Your beta 1 would always be negative. This value will always be negative. Is it clear, guys? Okay. So this example was for a univariable linear regression model. Univariable means like just one variable was there, one independent variable. But life is not that easy. I mean, you won't just find any such simple example. So something is called like multiple regression. In multiple regression, you have just one dependent variable, which is metric, like, as it's shown here. But you can have different set of independent variables, which could also be measurable. So nothing, you don't have to worry about it. You just have to provide the beta coefficient to each independent variable. So it's like beta naught plus beta 1 x1 plus beta 2 x2 up to beta k xk to the error term. That's it. So we assume that a relationship exists between y and k independent variables. So if you see, if I explain here, so you see there is only one variable, so you can there is only one y, there is only one x, so you can just measure that in 2 dimensions. Like this is y, this is x, right? But you cannot do the same in case of your multiple regression, right? So in case of multiple regression, as your independent variable increases, as your independent variable increases, your dimensions increases. So this can be explained. So if you have a k dimensions and you have one y representing which are dependent upon each k, which is dependent upon each x basically. So this can be explained in k dimensions. I hope I'm clear here. So here is like beta naught, beta 1, beta 2, and beta k are estimated method. So these are nothing but you are estimating these values, this beta coefficient, using different methods. One of them is least square method. I think you have read this method in your schools. So that is called something like multiple coding coefficient, and there was called like stepwise regression. So stepwise regression is nothing but it takes each variable, each independent variable at a time, and see if it is important and if it's contributing to your model or not. If it is contributing, it's keeping it. Otherwise, it is excluding it based upon their coefficient values. Basically, it gives the beta of 0. So when you multiply something with the 0, it nullifies. So basically, it remove that variable, and it only takes the one with the very high and very important contribution and beta with the beta values of or other contributions. Okay, so one of the very interesting one that we consider to make predictions when we have a dichotomous values. Dichotomous means the binary value, so like 0 and 1. I'll explain it. So if you're a dependent variable, if you're dependent, that means your y is dichotomous. I mean, it only takes binary values, right? So for example, you want to predict male or female, you want to predict diseased or healthy, you want to predict early or late stage, if you want to predict if it is for example, if a peptide is cancer or non-cancerous. So you always go for logistic regressions. Your independent variables could be anything. It could be metric, it could be categorical, it could be anything. I mean, it won't matter that which one is you're using. So this is the basically a formula of logistic function. This is nothing but the probability of value of x is equal to 1 over 1 plus e to the power minus y. So it's basically follows a logistic function where your values always lies between 0 and 1. So no matter however your x is varying here, your dependent will always lie between 0 and 1. That means doesn't matter how your independent variables are increasing, you can always represent a single row in the terms of probability, which lie between 0 and 1. That's it. So where you can apply this model, so you can apply the situation where, as I've said here, when your dependent variable is dichotomous. Dichotomous is nothing but a two values, a binary value. It could be 0, it could be 1. That's it. So it could be useful for the situation in which we want to predict the presence or absence of a characteristics or outcome on the basis of predictors. So predictors is nothing but your independent variables. That can be either numerical or categorical. As I've said, your independent variable can take any single value. There is no hard rule for them. So this is an example. So a useful way of describing the relationship between one or more risk factor, for example, age, cholesterol level, hypertension, etc., and outcomes such as death, which takes only two possible values, which is dead or alive. That's it. So dead or alive, there are dichotomous values. So this is nothing but your dependent variable. This is your y, which you want to predict, and you can use the values of age, which is a continuous variable. Your cholesterol is a continuous variable. Your hypertension is a continuous variable. So based upon that, you can come up with a formula, and you see if a patient comes to you, what you can do, you can ask him his age, you can ask him his cholesterol level, and you can ask him hypertension, and you can see that if that patient should live or not. Okay, as I've said, that largest is the probability of occurrence of an event that can be estimated by fitting the data. So basically, there's nothing. You are just providing a data. You are just providing a dependent variable. You are just representing the value into probability, and based upon that probability, you can say that what kind of label it should have, what kind of variable it should have. It could be like dead or alive. It could be 0 or 1. So this thing is very, very beneficial when you use machine learning. In machine learning, machine learning could be of different kind. I mean, it could be regression, it could be classification. In case of classification, you could have different levels, such as by classification, in which you're predicting only two variables, 0 and 1. Or there is multi-classification, where you are measuring more than one classes, like 1, 2, 3, or 1, 2, 3, 4, 1, 2, 3, 4, 5, anything. So these methods are very beneficial. So logistic function is one of the method you can use as a machine learning method. You can train your model based upon this function, and you can measure and you can predict the outcome from the variables which are unknown, or from the samples which are unknown. So yep, nothing. So this is nothing but I just given an example. So suppose there are three risk factors like age, sex, and cholesterol. So your age and cholesterol are the continuous, and your sex is discrete. It's a categorical variable, and their other one is not a categorical. It's a measurement scale. And we wish to predict the risk of a developing of coronary heart disease, which is CHD. So we are defining the CHD. So it's zero for no, 1 for yes. That's why it's a binary variable, right? So 1 means that the patient can develop the coronary heart disease, and 0 means no, it cannot develop the heart disease. So I have three variables: x1, x2, and x3. X1 is your cholesterol, 0 and 1. I mean, it's also categorical variable here. So 0 for low, 1 for high. And then I have age in years is a continuous variable. And then we have an ECG. Yeah, so ECG is nothing but 0 for normal, 1 for abnormal. And then we develop, so basically we are giving nothing but 1 plus e to the power minus z. So whatever value I'm getting from here, so z dash or z cap is nothing but a linear regression which fits which fits these three independent variables to predict your coronary heart disease. And using this variable, I can put this variable into this, and we can see 1 plus 1 minus e z dash, and we can see that if a patient is basically, what is the probability of patient to develop a CHD? So the risk factor can also be including like smoking status, diet, exercise, alcohol, and the coefficient can be estimated using maximum likelihood estimation. So based upon the sample, so there I was doing some analysis before, and I have a patient of 609 samples, and I was able to develop this formula. So z is equal to minus 3.911 plus 0.652 x1, 0.029 x2, and 0.032 x3. So you can see this x1. Your x1 was nothing but the cholesterol level, as is having a coefficient of 0.652. That means this is a very important one. I mean, this method or this independent variable is contributing the highest as compared to the other two, based upon the coefficient. And this is the second one. Yep. What's the question?
Yeah, I wanted to ask, have you incorporated other risk factor also in this equation, like alcohol and smoking?
No, I didn't do that because at that point of time, so this data came to me from the PGI, and they did not, they don't have the values for every single patient, so I have to exclude it. Otherwise, my number of samples would be less. So that's why I have to remove them.
Okay.
But you can always use that. But if you have such values, you can always include the risk factors as much as you can. So as I always say, that the more the number of variables you can use as independent variables, better model you have, the more better accuracy you can have.
Okay.
Great. So let's move on. So this is how you predict the z, and based upon the prediction, you can just convert that into a probability of 1 plus 1 over e minus z. So this value can never exceed 1 and cannot go below 0 because of the logistic function. So if you have like two patients, if you want to measure them in the risk ratio, so if you have like two patients, like category 1, his age is 40, or his ECG is 0, that means normal, so predicted risk is 73%. And in case of patient 2, if you put these values, you have a P is about 30.55. And if you see the risk ratio, you see that your patient 1 is at higher risk as compared to your patient 2. It just compare the risk ratio, nothing else. This is also termed as hazard ratio when you do the survival analysis. When you do the Cox proportional method, you see that you will use this method to define the patient is at higher risk or lower risk based upon the HR values. So there are other kind of functions available too, which is called linear curve estimation. Curve estimation could be anything. Quadratic. Quadratic is nothing but when your dependent variable varying is compared to your independent variable with a square value, basically. So something like that. There's compound, there's growth, logarithmic, cubic. You have a V-shaped curve, basically V-shaped curved, and then you have like S, your exponential, inverse, power line, logistic. There are different kind of estimation you can use. It's like multiple logistic. There's something called ordinal, probit, nonlinear. There are a number of methods which are like being popular these days, which are like nonlinear. As I've said, it's called be like random forest or support vector or decision tree based. So that there are a number of nonlinear methods which are being popular these days, because every single problem cannot be explained by linear relationships. They're like weight estimation, and then at the end your two-stage least square. So similar like that. I mean, people which are using these data like odds ratio. I mean, what are the odds of something being happening? So, for example, so odds is basically dependent upon success and failure. So, if suppose if the probability of a success is p, which is nothing, if we are measuring, we are having like zero 0.8, then the probability of failure is nothing but 1 minus p, which is like 0.2. So there are only so this exists only for something which like have only two outcomes, like success and failure. So what is the odds of success is nothing but p by q, which is like 4. So the odds of success are 4 to 1. And similar, like failure is q by p is nothing but 0.2 divided by 0.8 is like 0.25. The odds of success and odds of failure are just reciprocal of each other and nothing. So basically, when you do 1 by 4 is 2.25, nothing else. So if your success odds of success is 4, your odd of failure is nothing but 1 by 4, which is 0.25. So, and the odds ratio is basically tells you that how your data is varying. So suppose that the 7 out of 10 females are admitted to a medical school, while 3 of 10 males are admitted. So the odds of admitting a female would be 0.7 divided by 0.3, because the total female was 10. So the probability of success of admitting a female is like 7 out of 10, that is 0.7, and 1 minus 0.7 is 0.3, this is like 2.33. And odds of having a male is nothing but 0.3 divided by 0.7 is like 0.42857. So the odd ratio of admission is nothing but 2.33. That is the odd ratio of female divided by the odd ratio of male. Thus, the odds of getting a female being admitted are 5.4 times greater than that of for a male. So basically, you see here that how based upon the available data, based upon the available data, how's your what are the odds of something is being happening, right? So suppose if I'm giving a drug to a patient, so what are the odds of patient being treated or patient being beneficial of getting this drug compared to the one which are not having this drug? Something like that. This term is very, very, very beneficial when you use your different analysis. Suppose if you want to see if gene is beneficial in case of cancer or not, you can use this odds that you can see that what are the odds that this gene, X gene, is basically beneficial for the cancer patient or not. In case of case control study, you measure the association as odds ratio. So if you have like cases and the control, if you have like a number of cases which are exposed to some drug or exposed to smoke, and some similar like B number of patients are exposed, which are controls. So same as like non-exposed, you want to see that what is the ratio, what is the odd of exposure to the patient of a patient. So you use this formula, so nothing but A by C divided by B by D, nothing else. So A into C, B into D. You just divide it, and then you'll find the odds ratio. And you have a cohort study. You want to see the relative risk. So you have a cohort of exposed and non-exposed with the disease and not disease. So this is the incidence of disease: A over total number of exposed, C over total number of non-exposed patients, and this is how you calculate it. So A over A plus B divided by C over C plus D. But based upon this ratio, you can just tell that if your patient at higher risk or not. But if you want to see that if your method is actually, if your model is actually robust, or if your model is actually making some sense, so you find so this is a correlation. So basically it's a Matthews correlation coefficient, which which is highly used in machine learning methods to basically tells you that how your model works and how good your model is. Higher the value of Matthews correlation, so it basically varies between 0 and 1. So higher the value of your MCC, the better your model is. So if all the predicted and actual values only take two values, so suppose if you for example, you want to so let's say if I'm having if I'm having a number of peptides, and if I want to predict that if this peptide is cancerous or not, So it has only two values. Like if so it can predict, I can predict it as at 0, like non-cancerous, and I can predict it as 1, that is cancerous. But these are predictions. But I also have the actual values. The model, which model is the best one? So the best model is the one which basically superimposes your ground truth, that is the actual values, to your predicted values. I mean, the difference between your actual values and your predicted value should be minimum. So that is the best model. So the 100% accurate model is the one which actually predict, when there is no difference between your actual and your predicted values. So, but you can apply here some like Spearman correlation, something like that. But there is a method which is developed by Matthews. So to basically see the correlation between your predicted and the actual values is called Mechanical resolution coefficient. Okay, so there is so bear with me. There is something called these terms that you should understand first. So this is predicted positive, predicted negative. So this is what is predicted, and this is the actual. This is the ground truth, and this is the predictions made by your model, made by your equation. So true positive are the ones which are actually positive, and your method also predicted as positive. Your false positive is the one which is predicted as positive, but they were actually negative. You must have heard about type 1, type 2 error. So this is like type 2 error. Predicted negative. So if actual so false negative is the one so which are predicted as negative, but they are actually positive, and the true negative are the one which are actually negative and also predicted negative. So based upon these four terms, TP, TN, FP, FN, you can calculate number of different parameters to explain your model if it is good or not. So this is sensitivity. Sensitivity is nothing but it tells you the actual power or actual ability of your model to predict the positive samples. So it's nothing but sensitivity measures the fraction of actual positive which are correctly predicted. So TP upon total positive, that is TP plus TP plus FN, that is true positive plus the false negative which is predicted as negative, which are actually positive. So specificity tells you about the ability or the power of your model to predict the negative samples. So it's nothing but the fraction of true negative divided by actual negative. The difference between the model is the best if your sensitivity and specificity difference is very less. Suppose if I'm having a model which is predicting the positive samples with 100% sensitivity and 100% specificity, that is the best model. But suppose if I'm having a model with a 100% sensitivity but 0% specificity, the model is not good. It is biased towards the positive samples. So you should always try to develop a model which should have least difference between sensitivity and specificity. So this is also a measure to basically tells you that how good your model is. So in machine learning, you also use this method. You also use these parameters to tell that how good your model is and how better your model is. And these are also the parameters that you can use to compare your method with the other methods, the existing methods. Suppose you're making a new method, you're making a method which is based upon some already existing methods. But how can you show that your method is better than that? The already existing methods, right? So you use these different parameters. So now, so there is PPV. So like positive predicted value is nothing but a fraction of predicted positive, which is correct, and same as NPV, like negative value, like TP, TN upon PN. You can find all these formulas in the internet. So this is the formula of Matthews correlation coefficient, which is nothing but the actually predicted, truly predicted value is divided by minus the falsely predicted value. So TP into TN minus FP into FN divided by nothing but the combination of each one: TP plus FP, TP plus FN, TN plus FP, TN plus FN. So it's very easy formula to remember. So when you have a value of 1, that means your correlation is perfect. That means your method is perfect. I mean, that means your model is able to predict with 100% accuracy that which is so there is no difference between your ground truth and your predicted values. That means your model is perfect, nothing else. So now these things. So as I've said, that you have the you have the probability values. You predict the probability values using logistic regression, and using these predicted values, you are basically trying to predict the you're basically trying to get the true positive and true negative, false positive, false negative. But all these parameters, they are threshold dependent, right? Your TP, TN, FPN varies with the threshold. Suppose if I'm having my probability values varies from 0 to 1, right? So it could be like 0.5, it could be 0.1, it could be 0.3. Suppose if I'm having a threshold of 0.5, I'm saying like the values above 0.5 is 1, that is positive, and the point below zero point 0.5 is negative. So now if I'm having TP and TN, FP and FN, it has some values. Now suppose if I'm sliding my threshold to 0.3, so if I'm having value of greater than 0.3, they are positive, otherwise they are negative. That means my value will differ. My TPT and FPFN, these values will differ. And based upon these values, my sensitivity, specificity, accuracy, my MCC, the F1 and their kappa, they all are varying. So anyone can use these tricks and can show that my model is perfect based upon some very low threshold or very high threshold, right? I can show that okay, my method is predicting with 100% accuracy. My method is best. So there is a need to develop or to use some other parameters which can tells you that okay, this method is best, but it is not dependent upon any parameter. And for that, we have AUROC. That's called area under the receiver operating curve, characteristic curve. So I'll give you, I'll explain this with you some example. So there is an ROC is a graph showing the performance of classification. As I said, is the performance of a classification model at all classification thresholds. So all threshold, because it takes all threshold into consideration before tells you that if it is correct or not. So it's a plot between two parameters, that is true positive rate, that is sensitivity, and a false positive rate, which is nothing but 1 minus specificity. So consider the data for serum ferritin and a test of iron deficiency. So if I'm saying IDA is nothing but your iron deficiency anemia. So if I'm having a serum less than 15, number of IDA patients are 474, and number of IDA. So so you can see the threshold. I'm beating the threshold, right? And when I'm beating the threshold, my true positive and true negatives are varying, right? So anyone can use any method and then they can say that the method is good. But in order to, but AUROC is the method that you cannot cheat. So sensitivity and specificity for this test, we have to choose the cut. So we have to choose the cut point. So we basically separate the normal from the abnormal based upon if we choose less the value. So this is a threshold 34. So if a value is less than 34, then it's abnormal. If it is greater than 34, then it is basically your normal. So you calculate, yeah, you just put the values in the different formulas. So 649 is your true positive divided by these are the actual positive and these are the actual negative. That is 770. So these are correctly predicted. So 649 divided by 809, you have 80.2%. Specificity is nothing but this is being like 94.4%. So you see there's a difference between sensitivity and specificity. Your model is good, but your model is not best. And that's why your EROC won't be one here. So you have like 5 different cut points. You have like less than 15, less than equal 34, and then 64, and then you can see there are different sensitivity, specificity, and when you divide your 100 minus specificity, this is false positive, right? Or nothing. So you have these values, right? And now you can plot this value and you can see that how much your AURC is. So let's say, so now that sensitivity increases, the specificity. So as the sensitivity increases, the specificity drops, and vice versa. Compute 100 minus specificity, blah blah blah, whatever. So as this is increasing, this is decreasing. This is what I want to say here. So ROC curve is nothing but it's a graph between two axes. One is true, so your x-axis will be true positive rate, the sensitivity, and your y-axis would be false positive rate. That is no, the opposite one actually. So your x-axis is 1 minus specificity is false positive rate, and your y-axis is nothing but your true positive rate. So this is what you see. So you see you have one, two, three, four data points. So there is like four data points shown. I mean, there are more than four data points here. So you see that it's not perfect. It should be perfect. When it's perfect, it should be like this. I mean, the entire data, the entire area should be covered, and that is the best method. So when we did it, so you see the AUROC for this data, we have like 0.92. This is a good method. I mean, this is a good, but this is not best method. I mean, there are other methods which can predict with the AUROC of 1. So it has generally range from 0.5 to 1 with the following interpretation. So if you have like 1, it's a perfect test. If you have like between 0.9, it's an excellent test. It's a good test. But if you have 0.5, that's a random. I mean, any random values can achieve 0.5. And if you're having an ARC of less than 0.5, that means there is something wrong with your model that is not able to predict the actual values, or it is predicting the opposite. And it is a worst method. I mean, this is what I can say about it. So these are the values and these are the predictions. Now the last part of the talk is nothing but the hypothesis testing, right? As I've told you, why to check the normality is important is because of the hypothesis testing. So I have some hypotheses I want to test. Could be anything. I mean, it could be anything that it could be like if people the smokers are at high risk of the lung cancer. My hypothesis, right? So I have a data for that, and now I need to check if my data is following the normal distribution or not. And based upon this single thing, I will decide that I will go for a parametric test or non-parametric test. Parametric tests are nothing but they are the tests which are having a defined parameters. And why we are talking about normal distribution? Because normal distribution have two parameters. The one is your mean, and second is standard deviation. As I've shown before, that it's a bell-shaped curve where 99% of the value is defined between your mean and your plus minus 3 standard deviations. So that's how you use parametric test. And non-parametric tests, they don't have any assumptions. It is just a formula you apply, and that's it. So if your data set is following a normal distribution, yes, it is following normal distribution. So you go for primary test. And then how many samples? If only one sample, then do you know the variance? You go for the t-test. If you know the variance, then you go for the z-test. If the samples are paired, then you go for a paired test, otherwise T group T test. So the paired means if you have two values for different time different time points. So suppose if I'm having a patient, I give him a drug. So I have a values before giving the drug, after giving the drug. If I want to compare if the drug is beneficial or not, I can use it. If there is a significant difference of came into the patient and the patient's health after giving the drug, I will use the paired T test. Otherwise, I'll use the two group T test. Similarly, Pearson correlation is basically used when your data is following the normal distribution. Otherwise, you won't do it, and otherwise you will follow the Spearman rank correlation test. Similar, you can see that the same thing. You'll see there are like sounds. One sample Wilcoxon test, Kolmogorov-Smirnov test. This is the test for normality. The chi-square test, Mann-Whitney test, Wilcoxon test. So you have to decide based upon these conditions. These conditions that which one you should follow. The first thing that you should consider that you should follow the parametric test or non-parametric test. The worst mistake that people make these days is like they don't check the normality and they just apply t-test. That they don't check the normality and they just follow it and they report the results. But the result that you will report will be wrong. It will be wrong impact because your data is not following the distribution. So and because these parametric tests which are made, they are made upon the assumptions that your data is following a normal distribution. So these are formulas, nothing else. So when you give some value into it, so it will give you some value, it will give you some result. But how reliable that result is based upon your intuition, based upon your understanding of the statistics. That's why I said in the starting that statistics is nothing but an intuition. You have to have that intuition to basically run or apply some tests. So yeah, so parametric test, statistics, and where to apply. So the given observations are independent. They should not dependent upon each other. There should be no confounding variables there. Observations come from a normal distribution. That is the most important assumption, because your entire formula, your uh, entire assumption is made upon that assumption. The hypothesis involve population parameters. Parametric procedures may be applied on the measurement data only. So there should be a measurable quantity. The computation sometimes difficult, and they're robust in the non-parametric procedures, of course, because they have very significant, very stringent parameters, very stringent intervals to be followed. And there are different kinds of parametric statistics, as I said: Z statistics, T statistics, F statistics, chi-square, and one-way, two-way ANOVA, multi-way ANOVA, based upon the number of classes you have, 1 or 2 or 3. So if you have like 2 classes, you go for Z statistics, and you go for T statistics. If you have like more than 2 populations, if you know the variance, then you go for F statistics. Otherwise, if you have more than 3 classes, so if you want to predict, if you have a number, if you have a gene expression, if you want to predict that a patient have a lung disease, or a brain disease or liver disease or something like that, you can do that. But you can see that if there is a significant difference between the patient based upon that gene expression, is using one-way ANOVA, two-way ANOVA, multi-way ANOVA. So this is the T statistics, nothing but a single population mean, that you have already defined mu naught, and you want to see that if your sample is having that, if your so this H naught is mu equal to mu naught, that means that your sample mean is equal to your population mean. That's it. That's easy. It is. If you have a 2 samples, then you have, like, you will compare mu1 is equal to mu2. If your 2 samples are having the same population, the same mean or not. So the null hypothesis for this test is that if I'm having 2 groups, so my null hypothesis would be there is no significant difference between 2 population 1 and population 2. So if I get p-value less than 0.05, I'll say yes, I'll reject the null hypothesis, and I'll say there is a significant difference between mu and mu2. There's a paired test when you have before and after the values. There is a correlation coefficient that you can use. There is F statistics, which consider the population variances, and the chi-square values. So examples. So can we say that based on example, gene expression level is different from 50 fpkm? So my mu is 50. I want to see that if my mean is 50 or not. So does the mean expression level is in 2 regions different? So mu is equal to mu naught is the H1, your alternative hypothesis. Whether the medicine is effective in controlling blood pressure or not. So mu d is equal to, this is the paired one. So if you want to see that, I mean, before giving the drug and after giving the drug, how does that work? There is nothing but before taking the medicine and after taking medicine, d is equal to y minus x. Now the question arises that why do you need it? I mean you can just measure the mean, and you can just compare it. I mean, why do you have apply to this difficult test, right? So the reason is that, okay, so the reason that you are applying this test on a sample, and we don't know that if we have taken the samples correctly. So there is a table exists based upon different degree of freedoms, which tells you that what T statistics should have when you have a very large sample, when you have samples in millions. So it will give you some p-value in that, and based upon that p-value, you can say that with confidence. So the p-value is nothing but give you the confidence that yes, your sample is actually different or not. So that's why you need to apply the tests. Now the non-parametric test and where to apply. So these are similarly, the options are independent, but the population do not satisfy the assumptions underlying parametric tests that normality, independence, and constant variance. I mean, there should be no normal distribution. But in my own experience, even if your sample is following the normal distribution and you apply non-parametric test, it will work almost fine. Very less number of samples, it won't work. The hypothesis to be tested does not involve a population parameter, and the data has been measured on a weaker scale. So these are non-parametric tests. Fine test, Wilcoxon's rank test, Mann-Whitney test. So there is always an alternative of a parametric test in the non-parametric test. Chi-square test, Kruskel-Wallace, and Friedman. So here I've given the test. So these are the alternative, these are the analogs. If you have like one sample t-test in parametric, there is analog is signed rank or binomial test. Two sample t-test is Mann-Whitney test. Paired sample t-test is nothing but Wilcoxon signed rank matched pair test. One way ANOVA is your Kruskel-Wallace test, and repeated ANOVA is Friedman test. You can always use these things to basically to see that if which one do you use. I mean, of course, if your data is not following normal distribution, that doesn't mean it's the end of the world. You can go for the non-parametric test, and you can make you can tell people, you can give your interpretation based upon that. So now the disadvantages and advantages of non-parametric methods. The first one is they depend upon the minimum assumption. There is no assumption needed. There is no parameters needed. Computations can be quickly and easily performed. The methods, I mean, of course, there are no parameters involved, so their computation will be very easy. Non-parametric precision may be applied when the data are measured on a weaker scale or when the data count and the rank data is available. But the disadvantages is the NP tests are weaker than the parametric test in the terms of power. At the end, when you do some statistical data analysis, what do you expect? So the goal of the statistics is to gain understanding from the data, so that you can convey your thoughts. You can convey your claim that you're correct about your data. So this will be nothing but just to give you a confidence and to make you a confidence in the evidence that you're correct, your hypothesis is correct. And any data analysis should contain the following steps. Yes, first step is the formulate a research problem. This is the first step, and this is the most difficult step. You need to research. You need to formulate the problem first. You need to see that what do you want to predict and what do you want to see about the data sets. What do you want to convey to the people? Second step is define population and sample. I mean, you have to define the population in the sample. There are ample of techniques available in today's state, using which you can basically take out the sample from the population, because applying or collecting the data for the population is highly diverse and highly difficult. And next step is to collect the data, which is a very easy procedure, and you just need to enter the data into Excel sheets or different sheets or in Python or in the R, and you take further analysis. Then the first thing you should do is do the descriptive data analysis. Descriptive means you see the mean, median, mode, or your correlation and all such things. It's important to see that if your data is worth of giving time or not. If your data is crappy, then you should discard it, and you should change your research problem. You should move on to some different problems. And step 5 is use appropriate statistical methods to solve the research problem. As I've said, you have to see that if your data is following normal distribution or not. You have to see that. And based upon that, you apply your parametric and non-parametric test, and based upon that, you apply regression or non-regression methods, and based upon that, you give the model to the world to see that if you're correct or not. And at the end, report your results and claim that what you are saying is correct, and just give evidence to your hypothesis. So that's all from me now. Thank you so much for listening, and that's it. Thank you so much.